Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I would like to turn it over to Tony for the official program.
Thanks very much, Harold. Right. Okay, so this is an embarrassing slide again. I once had a PowerPoint presentation thing. You put your hands behind your back, look like a sergeant major, or like this, or like this. So it's very difficult to know what to do with your hands. Anyway, highlights of the eScience workshop. I've enjoyed it very much. Day one I would describe as environment and scholarly communications. And it started off with Drew Purves from our Microsoft Cambridge lab giving a keynote about uncertainty in predictions in climate science, which I think is extremely important. And then there were two great panels on open data for open science and big data for environmental informatics, and finally clouds and big data. So for me it was a very exciting conference day, and I feel that a lot of things came together and that we're on the verge of doing something significant and making something happen, it seems to me. Day two I felt was really about the data scientist. What is a data scientist? You know, and what do data scientists do? And in addition about citizen science and so on. So David Heckerman started with a joke. He gave a great talk about his work on genomics. It's titled Biology from Wet to Dry. He was, of course, referring from his move from Seattle to Los Angeles, right? But that was his joke. Okay. We had two interesting panels on data science. One was from the iSchool librarian-type perspective, and the other was from the computer science perspective. And they were very different. So I found that very interesting. To me, I found it a very interesting day, and I hope that you did too. And we all know a little bit more about things like data management plans and data curation and stuff like that. So the Jim Gray eScience Award is what we're here to do today. And so let me just first of all say a little bit about what the intent of the Jim Gray Award is. It's intended to be in memory of Jim for a researcher who made an outstanding contribution to the field of data-intensive computing. Jim had this idea of the fourth paradigm, the way you need to teach people new skills to deal with the flood of data that we're coming in science. And what he would have appreciated was innovators who really made science, the business of science, easier for others. So I think it's all summarized by the quote from Catherine Van Ingen at the bottom, who worked with Jim in the San Francisco office. Jim preferred doers over talkers. So I don't think I'd ever win the Jim Gray Award. Right. However, you know, we have a great lineup of Jim Gray Award winners here. Alex Saleh won the Jim Gray Award before it was called the Jim Gray Award. So we've corrected that, and Alex certainly, as a long-standing collaborator with Jim, should surely get the Jim Gray Award. Then we managed to surprise Carol Goebel, and Jeff Dozier, Phil Bourne, and Mark Abbott have all been worthy winners of the Jim Gray Award. What pains me slightly is that these are, if you look at our website, there's pictures of me giving a block of glass to these people, and I look enormously big in the photo. So you can trace my loss of weight through the years by these photographs. So to me, it's slightly disturbing. Yes, as long as it keeps going down, that's okay. All right. So before we get to the past winners, I'd like to celebrate some of the work that Jim did by asking Donna Carnes, who's Jim's wife, to come and accept a copy of Science at Microsoft, The Fourth Paradigm in Practice. I wasn't sure, Fourth Paradigm in Action. It could be misinterpreted. So in practice we used. And in here there are two of Jim's major achievements. One is TerraServer. And I don't know if you know TerraServer. Jim was the first to put up geospatial data on websites, and he won all sorts of prizes. And he couldn't get Microsoft to be interested at all in this. And he was working with a small company called Keyhole Technologies about interfaces for this. And then they were bought by Google, and so we created Google Earth. All right, so that was a great achievement by Jim. The next one was a thing he did with Alex. He got so frustrated by the discussions about the National Virtual Observatory in astronomy that he said, Alex, why don't we and a couple of students go and build something? And so they built SkyServer, which was for displaying the Sloan Digital Sky Survey data, and that was really exceptionally successful and has been the basis for disseminating open data to the public, to scientists, and so on, and is a model for many other things. So, Donna, I wonder if I could ask you to come and just accept this book. Thank you very much.
Thank you.
Very good.
Thank you.
So, thank you very much, Donna. So, to go back to these past winners, rather than talk about what they did, I'd like to show you a video. So, I think the next slide is video.
Jim Gray was such an awesome colossus.
He was always very interested in what other people did, and he really made you feel special when you were with him.
This is a collective thing. This is something we all deserve together because we're all pushing for the same thing that Jim had the original vision for.
I think Jim brought the best of computer science down to real-world problems.
Microsoft Research, since 2008, we've presented the Jim Gray Award at our annual eScience meeting.
So the Jim Gray Award is for work in what is called data-intensive science, but it means, I think, more than that, in that much of the data-intensive science has to be collaborative.
Collaboration is just essential because studying these complex systems, no one person can understand all of the science, all of the technology, all of the nuances associated with the data.
Essentially what was the essence of what Jim was trying to get across, which is the importance of this fourth paradigm and the idea that how we manage data and how we effectively use data and ultimately get to knowledge from that data and communicate that knowledge.
All of the people who have won the Jim Gray Award have done a lot to help other scientists do better work.
What I'm most passionate about is accelerating scientific discovery. My inspiration for collaboration is 14-year-old girls. 14-year-old girls collaborate big time. They're never off the phone. They're always on the websites. They're always doing Facebook. They're always twittering away. They're constantly gossiping. We need scientific gossiping. I applied Facebook ideas to collaborating and sharing of scientific protocols.
I'm an Earth system scientist. I study the Earth. I'm mainly interested in hydrology. The study of snow and the hydrologic cycle is important because so much of our water supply comes from melting snow. And worldwide, probably a sixth of Earth's population depends on snow and glacier melt for their water supply. That's over 1 billion people. Our group freely shares everything we do, all the measurements we make, all the data we collect up in the mountains. That way we sort of help science progress.
My area is mainly in computational biology, so I actually use computers to try and solve biological problems. I've become interested in scholarly communication and basically trying to address the question, can we improve the way that science is disseminated and comprehended?
Ocean science is trying to understand the ocean. I think it goes beyond that. It tries to see how does the ocean impact the entire planet? How does it interact with the atmosphere? How do things on the land affect the ocean? So when I first started out as a young PhD student, people would collect water in bottles and they'd get 200 samples. And those 200 samples would take 1 year to analyze. I, on the other hand, was using a computer to collect 8,000 samples, and it was analyzed within an hour. I think it allowed us to really look at the fine, detailed structure of the ocean and see things that we couldn't see by a sample every 200 yards. I think winning the Jim Gray Award is actually more a recognition of ocean sciences, and I hope that it will inspire other young scientists to use computers, to use information technology in new ways. How do you bring all of these complex and enormous data sets together? How do you bring people together? And how can I get better science by using computer science tools?
The future of eScience is about developing the tools to enable scientists to manage and understand data more rapidly and more easily. My hope for the future is that people won't be talking about eScience in 10 years' time because it will be the normal way to do science. So eScience will become science as we go to the future. So now we're going to go and announce the winner of the 2012 Jim Gray Award, and the winner should be no surprise to you all. It's Tony Williams, who has won the Jim Gray Award for actually making chemistry and chemical materials publicly available in a wonderful resource called ChemSpider, which enables the whole scientific community to access and interrogate and search chemical compounds. So can I ask Tony to come up to the stage and accept this year's Jim Gray Award? Thank you. How are you doing, son?
Great, thank you, Jeff.
Jeff Devlin. This is another photograph of me with a stomach, all right, you see? Okay. One more.
We extinguished it.
Thanks very much indeed. So let me just then introduce your keynote, and we'll take care of the award. So Tony is going to give a keynote on the possibilities and pitfalls of internet-based chemical data. I should just say a few biographical details. He was born in a strange country called Wales, which is part of the UK, and went to Liverpool University and then in the University of London before moving to Canada, where I think you've stayed in North America ever since. Is that,
yeah.
That's right. And besides developing this wonderful resource, ChemSpider, which he'll tell us something about, he's worked for governmental research labs, but also for companies, and done, it says here, software applications for spectroscopy and general chemistry, marketing, sales, business development, essentially everything. So can I ask you to welcome Tony to give the 2012 Jim Gray Award lecture.
Thank you, sir.
Thanks very much. You're doing great.
Thank you very much. Can everybody hear me okay? Coming through clearly? I have a tendency to wander, so I'll probably be up and down. And I'm definitely a talker as well as a doer, so somebody's going to need to warn me when I'm going over time. Show of hands, how many chemists in the room? Okay, I'm in trouble. All righty then. I'm going to tell you about what's going on in the world of chemistry online. One of the interesting things is look how many chemists we have in the room doing eScience. If you look across how much funding is going into chemistry, into cheminformatics, not bioinformatics, you'll find it's a very, very small amount of money. And yet, how many things do we know that don't have chemicals in them? Where do we not touch chemistry? This is a very interesting world where chemistry is just left alone in so many instances. So, one of the things I'm going to talk to you about is how a hobby turned into something much bigger. While I'm receiving the award, I'm sitting on the shoulders of hundreds of people who've contributed. I will introduce you later to one of my closest friends and colleagues who helped make this happen. The brilliance of what was done just in a basement. And I feel very honored to stand here and represent it. So I'm a chemist. I have done many other things, but I've definitely performed a few dozen chemical syntheses before I became sensitized and couldn't go in the lab anymore without getting all red and blotchy. Chemistry's good. I've run thousands of analytical spectra, so these are things with lines that we then interpret and turn into chemical compounds and structures. I worked at Kodak for a few years. I ran multiple labs at Kodak, millions of dollars worth of equipment. I've run thousands and thousands of them, and I've generated thousands of NMR assignments, and I'll show you a little bit about what that is later. And I've probably published 5% of everything that I've ever done. 5%. What a waste. All the stuff that I did that is decaying somewhere on an optical drive or has died on its disk that I can't even lay my hands on anymore. What a waste. But things are different today, right? We have ways of doing things differently where that 95% of work doesn't have to decay and disappear. And let's think about what that might look like. I don't know how many of you recognize that thing on the top left. That's a ZX Spectrum that had a big 16K memory load that I could deal with. The one in the middle on the top is a BBC Model B microcomputer, and I was programming in BBC Basic. The thing at the bottom on the left is an octal bootstrapped 620L computer that drove an NMR spectrometer where the cards were this big and the block was 4K, and we had 30 of them in a box because they used to break fairly regularly, and the thing stood this tall, and I could actually put in the octal bootstrap of 13 commands from memory and put in the paper tape that used to load the actual program, and then I would have to get on my bike, literally on my bike at 3 a.m. to go and change the cassette tape that would save the next 10 increments of my experiment, 1 to 10 between 5 and 3 a.m., and then 3 a.m. till the next morning, cycling 6 miles to do that. Oh, the good old days. That thing on the bottom right, how many of you remember Amstrad PC, Alan Sugar, and the gem maps? Yeah, show of hands. Wow, those were the old days, right? But of course, those were in the days when everything I was doing was just for me, because I was trying to create data that I could interpret and get a thesis and get the heck out of Dodge City. I grew up in a village of 60 people in Wales, and I needed to get out of there because there were only fish farming and chickens, truthfully. So I needed to get out there, and all I wanted to do was generate data for me, because there was nowhere to share it anyway. But if it wasn't just about me today, we might build an encyclopedia that we could share. We might be able to rate restaurants for each other so that I don't go to the bad place and get really poor food, and you might be reading good books that I should find out about, and on and on and on. And we do. We do this. We do it all the time. Well, maybe not all of us. How many of you here have written a Wikipedia article? Wow, that's good. Most rooms, I get nothing like that response. Congratulations for contributing. That's great. How many of you use Wikipedia? Human condition. We are more users and takers than we are givers. But we have ways to change that. We have ways to contribute, and we should be doing it. In terms of chemistry, more chemists might share data and share knowledge and information and learnings than take. That's what we'd like to see happen in the world of chemistry. So a hobby gone wild. 5 years ago, sitting with a friend of mine, Valery Kachenko, we sat down with a beer mat, and I bounced some ideas off of him about what we could do to change chemistry and data flow. Valery had some great ideas in the same vein. We're very parallel in some of the things we chatted about. With a group of friends, went off and built a platform running on 3 servers out of a basement. 2 hand-built using Tiger Direct components, 1 purchased from Dell. We begged, borrowed software. Thank you to Microsoft, we got an MSDN license. We're able to code up on SQL Server and using ASP technologies to put online a little database of chemical compounds. It was all late nights because I had a full-time job. So 10 o'clock till 2 o'clock in the morning, it was all about putting data together and coding up. We put this thing online in about 3 months and went live with 10.5 million chemicals. Those 10.5 million chemicals were sourced from a government database called PubChem. Many of you may know of PubChem. We went live and we got a few people visiting. I mean, literally a few. I wasn't in the world of the blogosphere at that point because nobody had tried to destroy what we were doing. Some naysayers in the community, some very high-profile naysayers, stepped up and said, this is not good, you shouldn't do this, you don't know what you're doing, and that's when the traffic started flowing. Don't look in the box, children, you don't know what's there. So, literally overnight, this thing went wild, and suddenly there were thousands of people showing up to see what we shouldn't be doing. And people started saying very positive things. It's great, I got answers to my questions, this is wonderful, keep it going. Then more and more data started coming online, and we started figuring out how to aggregate it and bring it in. And we did all of this, going live with 10.5 million chemicals and 3 servers running off of cable internet, with no formal funding, and was simply people who just wanted to do the right thing. It was literally just as a hobby. After 2 years and getting up to about 21 million chemicals and linking together hundreds and hundreds of data sources online and making a database that could be searched by chemical and text and substructure searching and all the things that chemists might want to do, the Royal Society of Chemistry came along and said, we would like to acquire this resource. That's great. What does that actually mean? Because one of the things we wanted to do was make sure that what we built wouldn't be acquired and taken away and closed down because it was a threat to other people. And what we were doing could have been seen as a threat. Royal Society of Chemistry has 2 aspects to it. It is a very, very good publisher in chemistry, but it's also a charity. So what they wanted to do was actually bring this in, support it, sustain it, fund it, grow it, and make it a rich resource for the chemistry community. So that's where I am presently and an extended team of cheminformaticians. So from year 2 to the present, ChemSpider, which is this database, has been running. And it grows on a daily basis. Literally, more chemistry is integrated into it every day. It's a central hub for chemists to add information, curate information, validate information, seek, search, browse. 28 million chemical records, and it's linked out to over 400 data sources. And it changes every day. And it's a hub. It's a central hub, and it's a container. So you can put in chemicals and properties that you've measured and movies and podcasts and. You just keep adding information into it. ChemSpider.com, feel free to go check it out. What we're trying to do is we're trying to answer questions for chemists. So those are probably not questions most of you will ask. Maybe the 2 gentlemen over here who are chemists might ask those questions, but these are the types of questions that chemists can ask. They can query about chemical compounds, they can query about properties, etc. Not in natural language, they can't type that in and ask that question, but they can say thymol blue, and it will find the chemical, and below it will be a whole aggregate of information. For example, a little chemistry first, because there's a room full of chemists that I'm talking to. I kind of knew. All right. Anyone know what that is? Yeah, it's aspirin. Of course, it's a small white pill. My favorite joke for my children is, why are aspirins small, white, and round? Because if they were big, gray, and wrinkly, they'd be elephants. But there is actually aspirin right there, and that is, anyone know that one? That's vancomycin. Probably many of you have had that. Firstly, that is not vancomycin. Of course, vancomycin is a small molecule with protons and neutrons and electrons and bonds between it that is a 3D geometry. That's just a representation that we use in the cheminformatics world to encode the detail about how atoms and bonds are connected together. I don't know if you can see the little laser, but these little wedges and hash wedges, they carry very specific information called stereochemistry. Stereochemistry in our world is very important. I'll show you why. This is what I used to do for a living. I used to acquire these things called NMR spectra, nuclear magnetic resonance. Don't let the doctors tell you that magnetic resonance was their invention. Not true. Magnetic resonance is from physics. Then the chemists stole it and started doing this type of stuff so we could determine what chemicals were. and then the doctors knock the word nuclear off because none of us want to be nucleified, and they have magnetic resonance to help us. But this is what I did, nuclear magnetic resonance. These data, all of these data lead us to this chemical compound when we interpret it. Years of training to get there. Does stereochemistry matter? That we have a solid wedge at the top and a dashed wedge at the bottom. That tells you something about the geometry of the molecule. Does one stereocenter in a molecule matter? Yes. The one at the top is teratogenic. It's thalidomide. It caused the issue with the children that we probably mostly know about. But thalidomide is a drug, and it's on the market today, but we know what to do with it better. But stereochemistry is very, very important. Certain drugs with certain stereochemistry are perfect for the body. Others are very damaging. So we have to understand this well. We have to understand this in databases. We have to encode it properly. These are different structural representations. The one on the right is a mol file representation. It is how atoms connect to bonds. It also carries, in this case, the coordinates of the molecule. Very, very common way of exchanging information. The one on the left here, these are called smile strings. Always puts a smile on my face when I see them. They are developed by different groups who have different software to generate them, so it's actually very difficult to go to a different software package and get the same smiles code. So that problem was picked up about 10 years ago for the two chemists in the room. Do you know of INCHI? Have you heard of INCHI? INCHI is the International Chemical Identifier. It is changing the way that the internet is linked together for chemistry. So these chemicals here are, again, serialized textual strings that represent that chemical. I can take these INCHI codes at the bottom and I can turn them into chemical structures. That is what I'm trying to search. This is the INCHI, International Chemical Identifier. It contains information about isotopes. It contains information about stereochemistry. Charge is something positive charged, negatively charged, etc. Very useful. And when the molecules are big, so if you remember that horrendous thing called vancomycin, it's extremely big, you get a very, very big INCHI. Hundreds of characters. And search engines online don't like hundreds of characters. They truncate them, and you've lost the value of this very unique chemical identifier. So what they decided to do is hash it into with this simple hash here, and it gives us a string that is always the same length and contains two pieces of information primarily. The first part of the hash is how the atoms and bonds are connected together. The second part of the hash contains everything else, stereochemistry, charge, etc. These are incredibly powerful. I can take a simple molecule now, generate that INCHI key, and I can start doing searches. For example, vincristine. Okay, this is the compound vincristine. If you go to ChemSpider and type in vincristine, you will get one chemical structure. If you go to Bing and you type in vincristine, you will get lots of pages. You won't necessarily be able to find the chemical, but you will get lots of pages because it's a text search. Here, what chemists want to do is they want to know what the chemical is. They want to know its properties. They want to know its synthesis. They want to know its patents, etc. So on ChemSpider, you would come to this page. Here's vincristine. We have some basic properties of the molecule, what its mass is, what its formula is, systematic name. That's generated using algorithms. And if I take the INCHI key associated with that compound, because everybody wants to draw that, right? Everybody wants to draw that very complex molecule and try and get every one of those bonds right. If you take the INCHI from under here, smiles and INCHIs, then you can start to search the internet for all of the information. Chemical vendors, publications. I really don't know what the bitch cheap encyclopedia is, but for some reason it is ranked 4th in importance for vincristine. But there it is, vincristine. Here we see vincristine information, videos, pictures, news, etc., etc. What I can do now is I can start to search the internet, not only by text, but by structure, by using this INCHI key search. You'll see how important that becomes when we try to link further information. Further down the ChemSpider record, we're going to find a list of chemical names. I will come back to these shortly because not Chemicals don't just have one name. Aspirin has over 400 trade names in the world. My favorite is Xaxa, X-A-X-A. That is a trade name for aspirin. It's a headache medicine for Xena, the warrior goddess, if you remember her. We have properties. These are experimental data, things that have been measured by people and have been loaded onto the database. Who says the melting point is 218 to 220 degrees centigrade? You have a link out here that goes directly to the site that says who measured it. It might say how it was measured. It might say the name of the scientist. It might be a publication. But the provenance is one click away in theory. We have predicted properties because not every chemical has had every property measured on it. We also have vendors, so you can find out their catalog IDs and you can click on their links and get out to their sites. We have lots of information such as toxicology, health and safety data, etc. Patents. You can take the chemical name and then you can hit the patents that are available, and patents are becoming increasingly available for free. So you can go download entire patent collections today, or in this case what we've done is we've hit the Google patents source with the name Vincristine and pulled back the list. But Vincristine is not enough because there are more chemical names that you should be searching on. That's why what we've been encouraging the community to do is help curate the data associated with these chemicals. Taxol is a drug from Bristol Myers. It is a drug for breast cancer. It's one of the world's best. However, it's also called paclitaxel and Utaxan. It has a cash registry number, it has an INEX number, and it has a whole series of systematic names. And if you want to do a complete search of the web for Taxol, you have to search it by all of its alternative names, all of its synonyms, all of its trade names. You have to search all of them. You will never get everything about that compound by searching its one name. So what we've said to the community is please come and join us and curate the chemical names. Add your own names so that we can figure out what to search. So in this case, we have a whole series of names, and when we hit them against APIs, then we can do these searches. So in this case, when we search something like Google Scholar or Microsoft Academic Search, for example, then we pass the entire list of names, and then we find all of those chemical associations. That's what it is. That's what ChemSpider is. It's a database of as many chemicals as we can integrate in. In order to make that happen as a hobby, it required the development of ways to input data, so bring in all the various forms of data and mesh it together. We would have to do some filtering in order to exclude bad chemistry, because as we know, everything on the web is pure, and there are no errors, and it should all be trusted. I will show you that that's not true, of course. We would then want to engage the community in saying, okay, if we do happen to pass some errors through to the database, please help us clean it up, validate the information so that we give better answers to the community. We want to give the highest quality data that we possibly can, i.e. closed systems that give you answers that you can never change are becoming more irrelevant. Don't give a system that you cannot annotate, you cannot curate, and you cannot contribute to. And that was the real basis of this entire project. Then, of course, we store the information, and then we index the data so you can do fast searches, text-based searches, structure searches, substructure searches. We would also present it through standard interfaces online, but we also realized that people would want to consume this data. They'd want to integrate it. If we did the job right, if we provided the highest quality data available online and gave people interfaces to use it, then it would be way more value to what we were trying to do. So, of course, we provided APIs into it and fast ways to search and browse, very powerful ways. Okay. So if you sit with your kids and you look at a cereal box and you tell them about how good vitamins are for them and you say, so vitamin K, then the question would be, let's go and find out what vitamin K actually is. Go ask that question online and see what happens. Well, in fact, there are several forms of vitamin K, and the one you're most interested in searching on is vitamin K1, which has, in this case, on the MESH, medical subject headings ontology, phytomenadione is the name. It's derived from plants. It's the one that we would like. So what's the quality of information about vitamin K1 online for a chemist? So the Merck index has been around for many years. It's very high quality data. It's curated. by a very skilled group of people. The quality of data here is very important. And what you should realize is that in this case, we have stereochemistry. Those two dashed lines are very important, as is the orientation around this double bond here. That's a very specific orientation. If we go to CAS, Chemical Abstracts, and we look at their contribution to online chemistry, they have a database online. It's a few thousand chemicals. We can find vitamin K1, and we can find that it agrees perfectly with Merck Index. CAS is very, very high quality, very highly curated. We have agreement here, good. So we say these two agree, let's take it from now that this is right. Now we start to compare things. We go to Wikipedia, it's wrong. There's no stereochemistry. Of course, a couple of clicks later and we've uploaded a new image and Wikipedia is updated and it's corrected. That's great, that's how it should work. Wolfram Alpha, it's wrong. In fact, if you go on Wolfram Alpha and you check for most drugs with stereochemistry, you'll find out that they don't know what stereochemistry is really. They don't use stereochemistry on any of the chemicals, last time I checked. For most of the drugs there is no stereochemistry involved. It's been reported multiple times, it's been there 2 years, and it's still not changed. DailyMed, for those of you who take drugs, not on the corner streets of New York, but actually from a pharmacy, they hand you a bag, just like on the corner streets of New York. Really. They hand you a bag, not that I know, and they have labels. Can you take that out of the video? They have labels, and on those labels sometimes are pharmacology information, and sometimes you will see chemical structures. And in this case, here's a chemical structure from the DailyMed labels, and it's wrong for vitamin K1. And by the way, it's not the only one. There are hundreds of examples of chemical structures and drugs going into labels being handed to us from pharmaceutical companies where the chemical compounds that they are putting in the bottles are wrong. It doesn't really matter so much as long as the drug in the bottle is right. That's what matters. But in this case, for chemists, they would like these chemicals to be correct. So that's DailyMed. And then PubChem, this is an old slide. When you searched on vitamin K1, there were 10 of those. And they're all different. They're all different. So some have stereochemistry, some have mixed stereochemistry. We have inversion of stereochemistry. But the search, vitamin K1, returned 10 chemicals at that point. Which one's right? People use trusted resources. For those of you who follow Derek Lowe, who has one of the best blogs in our domain around the drug discovery industry, for example, in the pipeline, this was yesterday, he blogged about amphotericin B, and he took the chemical structure from a trusted resource called Wikipedia. And Wikipedia is very good. I've worked on it. I've looked at many chemicals, atom by atom, bond by bond, and I've found a lot of errors, and I've helped change a lot of them, but I haven't caught everything because that structure is actually wrong. It's a trust taken from a trusted resource that is wrong, and of course, within a couple of hours of that being read, David Sharp, who happens to work in the cheminformatics group at RSC, and he's just as anal as me, thankfully, about the nature of chemistry. He went along and he actually edited the chemical structure and got it right, and now it's correct on Wikipedia. So how will that improve? How is it improving? How is all this stuff going to get cleaned up? Well, for open sites like Wikipedia, it's easy. You go change it, and you hope that somebody doesn't change it back, but that does happen. How does it happen on other databases where they're absolutely locked down, where the government doesn't actually allow you to make comments? And that's a very common position for the government. We host this, we're not responsible for what's in here, and we're also not going to give you a way to comment on it, even if you find an error. That's not really the right thing to do. That's what I've been told on a number of occasions where I've said, please just leave a comments box. We will get vandalized. People will say rude things. Well, we've been running ChemSpider for 5 years. We've been vandalized twice. A girl uploaded a photograph of herself and her friend under her email address wearing a university sweatshirt, so we know where she's from. And somebody tried to sell a house on with ChemSpider. Domoic acid. So one of those is domoic acid. They're all different. Every single one of those is unique chemically because of those double bonds and because of those stereochemical bonds, those wedges and dashes. It's actually that one. That one is correct. One would hope that the skilled experts in the field who are writing web pages dedicated to harmful algal blooms would get the structure of domoic acid right, and every single stereo bond on that molecule from the experts is wrong. It's inverted. And Wikipedia had it wrong, and many places have had it wrong, but we can't change that. We've told them, but we don't think it's changed. You have to question everything online, of course, other than information about Britney Spears, because all of that's true. DHMO.org, scary website. It looks very EPA-like with its logos, and that's dihydrogen monoxide. That's H2O. Long periods of immersion will result in death. It's true. If you ingest large amounts, you will die. Also true. And if you go on Wikipedia and you read about the DHMO scandal, you will hear about the politicians who tried to ban the use of DHMO in industrial processes, because chemistry is a nasty thing. We shouldn't trust it. So one of the things we did on ChemSpider is when we opened it up, we gave access to all of these chemicals, and we said, come along and help, please, because we're this little skeleton group working between 10 o'clock at midnight, 10 o'clock till 2 a.m., and we cannot catch all the errors in millions and millions of chemicals. Certainly we're not measuring all the data. We don't know your chemistry as well as you do, so please help. Anybody can annotate a record. Anybody can deposit data as long as you register, because if we see that there's issues with the data, we want to tell you. And register users can validate the existing data. So that became very important. Here's an example. You do a search on vitamin H, and you find 2 chemicals. The difference between the top one and the bottom one is the presence of stereo centers. These are very important, as I said. So these 2 bonds right here. The issue is that the word vitamin H is associated with the wrong chemical. It's okay to draw molecules without stereo centers, but to add the name and associate it incorrectly, that's the error. So you just need to remove it. In this case, all you do is you check the two boxes that says remove biotin and vitamin H here, delete it and submit, and they're gone. They're removed. They're still in the database, but then they're not going to return any hits if you search on them. So now we've just taken the one erroneous record out of the database. Now you need to do that for 28 million chemicals. You need to check them. You need to validate them. You need to validate every physicochemical data point. You need to measure every melting point, every boiling point, every log P value, every association with every article, and do it over and over and over again. When the database is growing day by day with new data coming in from numerous sources. Good luck. And if we don't start, we will never fix it. And that's the point. And my friend here, Carol, always says in difficult sessions, yes, accept we have a challenge and get to work. And that's the point. So we got to work. When we built the database, we then put on the web services. This is just a set of web services that are available. And people started integrating against it. As an example, mass spectrometry vendors, people who have million-dollar instruments who take things like human urine and they shoot it in the nozzle and it fires down and it fragments and you find out information about chemical structure. What they do is they take those data, they process it down to a certain point, they fire it over the internet using web services against ChemSpider. They pick out of the 28 million molecules a slice of data that would be associated with human metabolites, and they automatically download a series of chemicals, they put it out in a report, and it spits out the other side. Think of the ability to do that at the Olympic Games, where you literally take a runner's urine, spike it, and it comes back and it says, you've got chemicals, bing. That's the type of thing that we've been enabling. And Bruker and Waters and Agilent and Thermo, all billion-dollar companies, have been doing this against a public website. Very useful for name and structure resolution. If you want to know what domoic acid is, hit domoic acid as a query on the web services. Structure and substructure searching to support sites that need to do that type of thing for the chemists, but can't afford or don't know how or have never built a database of chemicals. But they would love to use one and integrate one. And for an innovative medicines initiative, an IMI project out of the European Union, these web services are being integrated into that project. This is the Open Facts project. Open Facts. Yes, we know it should be an F, but it's Pharmacological Concept Triple Store. It's a semantic web project. It's 36 months. The initial group that was involved, 22 partners, 8 pharma companies, 3 biotechs, continues to swell literally monthly as people realize that if we can integrate chemistry and biological data from multiple data sources, most of them public domain, but not all, if we can integrate them all together and provide to all drug discovery chemists in the world a way to query all of that data simultaneously, then we have a way to help them in their projects. What's been happening in the pharmaceutical industry is people have been downloading all these public domain resources and going through their own processes of homogenization and filtering and mapping. They've all been doing this work over and over in different companies. Well, it's public domain data. Why not choose to work with a group that can actually do this for them, where they actually participate, so the pharma companies sit at a round table and help design it, where we do it together, and then they all get to use that single system. By the way, because we're working, if you see the bottom here, the guiding principle is open access, open usage, open source, and also open data. When the project progresses, they will be able to download multiple open source components that we've developed. The open data that we've meshed together and integrated, they will be able to bring it back in-house and integrate it to their own systems. This project is going extremely well. We're already halfway into it, and the public release version, the first public release version, is imminent. So please keep your eye out for the Open Facts project. And of course, part of what we're contributing to the project is access to 28 million chemicals on ChemSpider, but also slices that are dedicated to the drug discovery industry. We're contributing into the semantic web using RDF, access to the entire database, using standard formats and standard ontologies so that people can access it. By providing web services, we enable clever professors like Andy Lang and Jean-Claude Bradley from Drexel and Oklahoma to come along and build games. So they took the spectral data off of the ChemSpider site and they said, okay, we're going to help students understand how to interpret spectra. So they made spectralgame.com. And it's tricky, because if we now watch students play on this game, what they're doing really is they're looking at the spectrum and they're trying to decide which molecule fits best. When we see errors show up, if a particular spectrum always gets flagged wrong by the students, the question is why? Is it difficult? Is there something wrong with the data? By allowing them to play their game, we get to curate the data. We found spectra where they've been flipped, and the way it was exported from the instrument is flipped. They're curating the data by playing a game. That's great. It's a great assist to us, and it helps us improve the quality. We are evil. We use students. So the world of contribution, things have changed. We are contributing in different ways. The immediacy of social networks, whether we know it or not, there have been tweets going out of here that have been saying things that are showing up and being indexed, and people make comments, and then they learn from you. Commenting on articles and data is here. In some cases, it should be better. The participating scientist has a high profile. The participating scientists, names that flow around the social networks that are connected to science, are getting much higher profiles in many cases than people who are doing really, really good science, extremely good science, and not participating in the social networks. That's an interesting phenomenon. With time, this will change. This generational shift is happening now. We will see more and more younger scientists participating in a different way. And by young, what do I mean by young? Anybody recognize that young lady? 10 years old. And she has a peer-reviewed publication already in computational theoretical chemistry, because she was making models at school and put together a molecule that the teacher lifted and went, wow, that looks feasible. And they went off and did the calculations, and it's a new class of molecule that they're actually written up here. Clara Lazan. And fold it. This is where you have proteges in the world of protein folding. So you can actually sit. In this case, this gentleman sits with his family in different rooms, and they fold proteins online. This kid is 13 years old, and he's in the top 10 of protein folders in the world on the game. This is a publication I was involved with reviewing a few years ago. So one of the things I did for a living was I measured NMR spectra, but then I worked with a company who predicted NMR. You would draw a chemical and you could predict spectra. I was asked to review it because the product I managed actually was reviewed as part of the science. So if I'm willing to look at atoms and bonds, you better believe that that type of table gets me going. Okay? So I actually looked at every one of those shifts for my particular product, and I found that. And if you look at the pattern, you will see that even to you, it stands out fairly obvious that if this is the experimental data point here, that it maps onto 142.7 very well. 132.8 maps onto 133. These are experimental numbers. These are predicted numbers. These are experimental. Switching those two numbers went from moving the product I managed from the 7th worst performer to the top. That was important for me and the company that I worked for. So during the review process, I wrote it up and I said, okay, there's an issue here. I can explain why it happened, but this needs changing. And of course, it was ignored, and the publication went out. And what do you do in the old days when that type of thing happened? I wrote a letter. I asked for a rebuttal to be published, and I was told by the editor, I'm not getting into this with you because you're in the commercial world. Ow. That was painful. 2 years, over 2 years. And then I finally convinced the author of the publication to work with us to clean this situation up. 2 years of work just to deal with 2 data points getting switched. Hexacyclinol. Hexacyclinol is a career destroyer in some cases. What was said was that this was an actual molecule that had been isolated. A chemist stepped forward and said, I have done the total synthesis of this. Here's all the data, published it. Somebody else came along and said, well, there are alternatives to that, and we believe that it is this chemical on the right, Scott Rickanowski, as I believe, did the prediction of the NMR spectra. Again, I'm an NMR jock, so I was interested. Did the prediction of spectra, and the agreement was much better. And the blogosphere took hold of this, and they absolutely went at this. I don't understand the hexacyclinol blog by Viagra Online, but you get that on almost every search, right? But here you go, hexacyclinol, pages and pages and pages of chemists who weren't really involved at all with hexacyclinol, looking at the publication, looking at the data, reviewing it, getting into the nitty-gritty, and engaging in discourse, watching this scientist trying to save his career. This is another one, oxidation by sodium hydride. So it says you can oxidize secondary alcohols in the presence of sodium hydride. Sodium hydride is a reducing agent. It does the opposite. Very interesting paper. What you have now is it says the manuscripts were being withdrawn for scientific reasons. Very helpful. What were those scientific reasons? What was said that was disagreed with? Who disagreed with it? Why was it wrong? How is it being checked? That is not the best way to deal with science, in my opinion. But the blogosphere dealt with it anyway. So they really got down to grips with this. This publication came out. Literally, the conversation started waking up. People were repeating the science and putting it up on their blogs. I don't know if you can see it. I don't know how accurate views are for blogs, okay? It does say 132,000 views of a blog post. I wonder how many times the paper was actually seen. 270 comments, 211 maybe. An entire blog post dedicated to this by a guy called Paul Doherty. He's got photographs of him repeating the synthesis. He's got his analytical data here. It's real. But how much of chemistry, well, how much of all science has already been done in some form that we can rediscover if we could figure out how to search the archives and how to pull more and more data out of the archives and make more available in different ways? Turns out that in 1946, this was reported already. And is much more relevant than the work that was being done right now. And Open Notebook Science, ONS. In this case, they repeated the work, and they kept timestamp and date stamp of every step they did in the work. Literally every 10 minutes they were working on this, they would be putting information online. It goes on a wiki. They got movies of the work being done. They repeat the work. And the result, of course, is that the publication is gone. This is more interesting to read about where the science was wrong than just it's been withdrawn for scientific reasons. So the scientific records are going to change, and that's good for all of us. This is Jean-Claude Bradley. He is, in my estimation, a guy who's catalyzing change in open notebook science for chemistry for sure. Drexel University, what this gentleman has kicked off as a movement we're going to see more of with time. Openness, so open source, open access, open data, open notebook science, licensing. Very confusing for many people with very many licenses to look at and adopt. It can get very challenging, and this is simply going to start settling down for all of us. What's mostly going to happen is that when public funding is being put into science, there's going to be a demand of the funding agencies, and it's already started, open access publication, make your data open within a certain embargo period, and data will come online, and then we can do more with it. We've suggested rules for licensing data. So this is a publication that was put in PLOS recently. I'm not going to worry too much about the rules that we have. They're very, very simple in many ways. But I do have at the bottom there, bolded, the term public domain. The public domain has a particular definition also. And we used it loosely. 3 of us wrote the article, this article. We used it loosely in the abstract, to the point where you get so close to an article, you miss what you're writing about. And we should have said publicly accessible database, not public domain database. Public domain got us in trouble. So this guy, I'm sure, yes, here we go. Carol and Caitlin are already laughing. This guy, Egon Willighagen, came up and says, okay, you said public domain, and Egon is one of those guys who will hold us to task. He called us on it on Twitter, and he was right. We loosely used the term. We didn't expect to get away with it, we just missed it. So fortunately, I live in a different period now. 2 years to change 2 data points, and I had to work with the author. In this case, I was the author, fortunately, but anybody could have done it. I came along and I left an annotation on the article. It took me 60 seconds to do it. I highlighted the term domain, and I said, please remove it. We messed up. And there I am. I'm Chem Connector on Twitter, etc. There I am. I've made that contribution to that article. It's there for everybody to see. That's great. Now, if that was somebody else's article that I'd made that annotation on, other than confessing my own sins, it would be really nice to be recognized for that contribution. It would be really nice to come along to read some articles and say, I have a different interpretation of this. What about this? Those types of contributions that we can all make now, how do we get measured on them? If we make these contributions, how do we get recognition? We'll come back to it. This is another publication I'd like to annotate. Has anybody ever read apoptotic gene therapy in the interdigital web? Anybody in the read? It's a classic. No, it really is. No, it's a classic, because that's what the interdigital web is. It's the skin that shows up between the fingers. And this article is about a guy who went on to become a regional swimming champion whose name was, oh my God, I swim fast. Aha, you got that, huh? Yes, it was wonderful. And some of the other highlights from the article were, we established a collaboration with Professor Something Wang, a fugitive from the Korean university, Who You Hiding? And at the bottom, identified as the new protein, Why So Dim? Go read it. It's a great article. But it just hangs out there as maybe an April Fool's joke, who knows? But I'd love to say, why so dim? Are you reading this? Things like that. But there's no way to annotate that one. We're in a new world for publishing, right? Blogs, wikis, micro-publishing sites. Here's an example. So there was a famous sporting event that I can't name for risk of the things that were going on in London, that are associated with a particular symbol. And we decided it might be fun to make a molecule that looked like that. That is that molecule. That's a single molecule atomic force microscopy image from IBM. So it was synthesized at the University of Warwick. A sample was delivered to IBM, and they took a photograph of a molecule. Very, very cool technology. But what the highlight we wanted to do was say, okay, we're hosting all these chemicals. We'd like to host syntheses. So we have a site called ChemSpider SyntheticPages. Again, I only published less than 5% of what I did, but I did all these syntheses. Wouldn't it be great if all of this wasted synthetic work so-called failed reactions are a good one. Is any reaction a failure in terms of learning? No. Don't do this. It doesn't work is a great learning. Right? So we wanted to set up a site where you could host synthetic pages, reaction syntheses. So we do. You come along, you log in, and you follow a template, and I added this to this under these conditions, and here's the reaction, and this is how we did it, and here's some data. And this guy puts six steps towards the synthesis of this molecule. All open, all available, all freely searchable, with DOIs, digital object identifiers that they can put on the CV, with thousands and thousands of views, immediately available for anybody. But they are peer-reviewed. They're peer-reviewed in two ways. The editors of the site, and this is a group of organic chemists in the UK, they review everything and give him feedback. These are going up in 24 hours, generally. And then the community, who can leave comments and say, I repeated it and it failed. I repeated it with this solvent, I got a high yield. It's a new way of publishing, with fully interactive data that can be downloaded under open data licenses and put into your own work. When you have this type of capability, now you have a new route to scientific recognition, because it's not just going to be about impact factors from peer-reviewed publications, of course. How do we measure a scientist? What do we measure them by? How do the funding agencies measure them? How do the institutions that they work at measure them? What's good, what's bad, what's right, what's wrong? Depends who you ask. Publication profiles, impact factors, index, HMG, I10, some of these I don't even know what they are, but I found them online, grants, etc. Scientists are notable in very different ways. I got into this discussion with Wikipedia about why are porn stars more notable than scientists. It went viral because I asked the question, why, when I can write up an article about a scientist who has an impact factor, an H factor of 45, does Wikipedia not deem him to be notable? When he has 7,300 citations to his work, is he not notable? Every article I wrote about a scientist that I thought was notable was flagged for deletion. Interesting. So I got into a battle with them. Those scientists' articles are all up now. However, as a result of that particular battle, I said, this is ridiculous. You can't write an article about yourself on Wikipedia. Maybe that's right, maybe that's wrong. I have my own views on that. But we set up a separate database called scientistsdb.com. We took Wikipedia articles on scientists and we moved them into that particular wiki. And we said, please, if you are a scientist, go add yourself here to ScientistsDB. Then let the community write your article for you on ScientistsDB. We're not going to criticize you. And then when it's ready, we'll lift it and put it onto Wikipedia for you, and we'll see what happens. So if you want to be on a wiki about scientists, go to ScientistsDB and see if you want to add yourself. Wikipedia has some very interesting editorial constraints. Public profiles are changing. Wikipedia is one. Somebody laughingly said, in order to be a scientist on Wikipedia, you need to die. I'm not sure that's true, but there's some measure of that. Online tools are now tracking activities of scientists. Whether or not you know it, you are being tracked. You are showing up in various ways on sites. Some are totally opt-in. You have to say, I want to be on this site, and then you have to fill your profile. But an increasing number of them are about you, and you might not even know you're there and represented. I would recommend that you find out, and you take responsibility for your public profile, because it's being built for you, and sometimes it's misassociated. And I would actually build your public profile. Microsoft Academic Search. For those of you who didn't know Lee was a wonderful man. I've met with him many times. I've had a lot of fun with him. He sounds like a dangerous gentleman to spend an evening with. That's him on the left. Lee was directly associated with Microsoft Academic Search. Great platform. Here I do a search of myself, and I see information about myself. There were 3 of me. There was a slim one with 6-pack abs. I wish that was me. But no. But there were 3 of me. One of them I had to say, those papers are not mine, and move them off, because I had the ability to annotate, curate, modify. And there was another one that was separate from me that I actually merged in. Beautiful tools for seeing my co-author graph. It's a brilliant way at looking who I've been working with. So question for you. How often do you see errors where you have not been able to annotate or curate and you wish you could, but it's too much work to send an email, so you leave it for others to work with? How many times have you done that? And how many times have you chosen not to annotate or curate, even if you could? I would encourage you, if you see an error, please participate. It makes things better. For example, anybody here know Rajarshi Guha will know that that's not him. But it's a photograph of him, and he works at the National Institutes of Health, and he has some publications, but in fact, that's Rajarshi. I know him well, so I actually pointed to the file that says this is a photograph of Rajarshi, and in the next couple of days, Microsoft Academic Search will make that change, and it will be resolved, and I will be responsible for it. And Rajarshi said to me on Twitter, I'm glad you're doing the work for me. At least it was somebody famous. And I don't know if any of you know that guy, but this is another form of me. This is happening for me. I'm not aware of it really at one point. I just showed up one day. So this is the Google Scholar Citations platform. What I like about this is that, again, easy to curate, so I could remove articles that are not associated with the other Anthony John Williams. And I could also, I get emails telling me that people are citing my work in Russia. Very useful to know who's talking about what I do. This is going to change with Flowers for Scientists. Of course, orchids, not the spelling of O-R-C-H-I-D, but O-R-C-I-D. This is the Open Researcher and Contributor ID. Every scientist is going to get a unique scientist's identifier. Once you have that, you can do clever things. It's like an INSHI for scientists, unique. It's going to enable you to aggregate activities. So if you participate somewhere on the web and you use your ORCID ID to log in, they'll be able to pull all this information together. If you do something on Wikipedia, they'll be able to pull it if you've got your ORCID ID associated. This is going to lead into alternative metrics about how you are measured as a scientist. It's the alternative metrics to you rather than the impact factors. It's your impact factor in many places. This is Jason Priam on the left and Heather Purwar on the right. They just released Impact Story. This is going to talk about the impact you are having in very many places. As an example, these are my publications. You can see what's highly saved, what's highly discussed, what's highly cited. I participate on SlideShare. My presentations go to SlideShare, Impact Story picks it up and starts using that information. It knows who I am. When I have an ORCID ID that's on my blog and on my Mendeley profile and on my Microsoft Academic Search profile, and I'm working on Microsoft Academic Search to make curations and annotations and edits, that will be fed out by ORCID. Then you'll be able to see this type of information. Here it's simply citations on Wikipedia, PubMed, Sciverse, and Mendeley. That's part of my impact story. This is very early. It's only been online for a couple of weeks. But imagine now if it participates in the connections to data. What data are you putting online? What data sets are you contributing? What are you doing on ChemSpider? Are you depositing chemicals? Are you depositing spectra? Are you annotating? All of the places that I contribute may all come together to talk about my impact on science. And of course, publications themselves are changing to deliver article-level metrics, not just impact factor details from the journal, but article-level metrics about how many times has your article been read in the past couple of days, how many times has it been cited, how fast, all flowing, connecting the web around you as a scientist. So the new measures of impact, whether or not they're numbers, we don't know. The bottom, we have clout on the right. We have ResearchGate score on the left, and not yet another site. And of course, Patrick McGowan in the prisons would say, I am not a number, I am a free man. But we are going to be defined in very different ways. But you will be measured on publications, data, algorithms, open source code, etc., etc. All of these will be aggregated, not just the publications. A lot of the challenges we have ahead are not actually about technology. Technology was always moving, we can contribute. We're not adjusting as scientists to a lot of the things that we can do, even though the technology will allow us. Growth in data, compute speed, storage, these are all growing. They will handle us. We shouldn't worry about it. Ontologies, dictionaries, trusted sources, these are all growing too. The challenges are about us mostly. How will we adapt to licenses and rights? What will we expect as rewards and recognition? And will we participate, contribute, and mostly will we collaborate? Because collaboration is key. Government labs are not collaborating the way they should. There are glass walls where public compound databases are being built independently. They're not even working together, and they're putting low-quality data online as a result. This is an example of what happened in the past few weeks. NCATS has released 58 identifiers of molecules that they want people to work on. They want to figure out if they can repurpose these drugs for the good of the humans. However, they put it out this way. And if you want to do computer modeling, you can't model AVE5530. You can't take a set of text strings and say, figure out if that docks into a protein pocket. It doesn't work. They didn't release the chemical structures. It's taken weeks and weeks and weeks to figure out just 30 of those molecules by hunting through the internet and curating the data. There was no reason that this had to go out. The pharma companies should have kicked these data in to this project, but we're very protective still. So what does the future hold? Maybe on Second Life in a couple of years' time, I will have a six-pack, abs, and I will be 6 feet tall and blonde and slim. And I will be attending these poster sessions, and this is the Aldrich store right here on Second Life. Maybe that's the future. I hope not, because I like people. The link network is going to continue to grow. And the data are going to flow around this network extremely quickly. So the quality of data we're feeding into it has to be dealt with. The deluge is not going away. It's just exploding. It's overwhelming in so many ways. We're trying to do certain things for chemistry. We're trying to deliver a chemistry hub right now. It's going to take us a couple of 3 years to build this thing. We intend for it to be a primary source for people to use for chemistry, where they can access information, not only about small molecules, everything I've talked about small molecules, but materials and polymers, and materials that we can't even talk about what it looks like. We know it has a whole set of analytical data. We know that it affects X, Y, Z, but we don't know what it is. But that information, how would we capture it? We're going to go across our entire RSC archive. Every publication we've had since 1841, we are going to data mine using text mining approaches. We're going to pull out chemicals, reactions, properties. We're going to make it all publicly available. Do you think there will be any errors? Of course. So we're going to put on a layer of curation called the Challenger Project. The Challenger is going to ask people to contribute and how to improve the quality of data as they read a paper. If you see an error, flag it. Please participate. And when we pull all this data together, we're going to have new ways to query it and enhance it. We're also going to invite any other publishers to participate. We're going to be able to segregate our data into pockets. We'll federate a data search across everything. But there are reasons to go into specific areas of chemistry and ask specific queries. We're going to provide a platform for people to put their personal data. You can have public data, you can have private data, but we will host it. Institutional data. And the institutional data could be an entire organization that can collaborate on their own private institutional data and then flag it and release it to the public. And it's an enormous architectural change for us. Enormous architectural change. We're going to have to deal with a whole lot more expectations around how to serve the data up, how to flag the data, how to qualify the data, etc. Data validation is exacting. This is one single chemical. And look at the variation in melting points from different sources. To figure out which one of those is right is very, very exacting work. It takes time. So we're going to ask for thumbs up, thumbs down, simple Challenger approaches. Which of these is nystatin? Somebody has to come along and do the work and tell us what's right. We're going to provide interfaces on mobile phones so that when you're sitting in an airport, you can help curate the data. It's not just small molecules, we have to deal with the complexity. The delivery of the document, so you'll be reading articles, you'll be able to map, do plots in real time, you'll be able to edit the data, you'll be able to flag data as what's real, what's unreal, what's invalid, generate algorithms from it, take the algorithms out, publish them out to the wild so that scientists can now use these algorithms for their own purposes. And while it looks a little colorful, that's what articles are already starting to look like. Markup technology that links things together. So, I don't know how many of you read my abstract, but maybe there was an error. maybe that shouldn't be glisters, right? It should be glitters. Well, actually, depends. Because if you go on Wikipedia, you'll find all the glitters is not gold. But for those of you who ever read Merchant of Venice, the derivative is actually glisters. But wouldn't it be great when we're reading things now where there are chemical names from 1840 that nobody knows what that is? Nobody knows what that chemical name from 1840 meant. That you can actually just mark it up and map it to the real definition of today. That's the issue with trying to map old, antiquated chemistry into new chemistry. Thank you so much for the award. I feel very honored to be here and represent the work of hundreds and hundreds of scientists. I work at RSC. The RSC Chem Informatics team make my day a joy. We get a lot of stuff done. We have a lot of fun. There are so many people who have provided data that I've never met and will probably never meet. Curators, annotators from all around the world, software providers, commercial, open source. There's such a large audience of people who've made ChemSpider work. And I have some trusted advisors in the open notebook science world, in the pharmacology world. Lee Harland from Open Facts, Carol Goebel here who works on Open Facts, and this guy. And this gentleman is my friend and colleague, Valery Kachenko. He's sitting right down here. He might look a little older than he does in that picture. As you can see, we're well aligned. We have exactly the same angle. It's very interesting. We'd love to talk to you about where we're going with chemistry and the new architecture and what we think we can contribute. And if you'd like to talk about it, we're going to be around. And with that, thank you so much. I greatly appreciate the opportunity to tell you what we've been up to. Thank you.
Thank you very much, Tony. So I think we'd better collar Tony for questions over a beer after the event. And so shall we take a few questions now, or shall we postpone them for afterwards?
Either way.
I think why don't we take 2 questions now and then the remainder afterwards. Are there any questions that people would like to ask of Tony? He's presented a great vision of where we should go. Yes?
My question is, for a talk, it was very nice. I'm a computer scientist, and chemistry is always far from me, but very interesting talk. My question is, how many librarians you have in your project, and how many digital librarians or metadata people are helping you with that work?
How many librarians?
Yeah, librarians. Yeah.
Well, we have librarians out there in the wild who are actually looking at the data, but in our own internal project.
You don't have any?
RSC doesn't have a librarian?
We have librarians that are down in a separate building from us, but in our Chem Informatics team, we have no.
They don't talk to you. They should.
Thank you.
We talk to librarians. We've just had a meeting with them. So.
Very good. One last question. If not, let's conclude the talk by thanking Tony again, and I suggest that you are inspired by what he's done in chemistry, and we should clearly do it in other fields like environmental science and biology and so on. So let's thank Tony again for a great talk. So, very good. Thank you. That was great. Thank you. Well done. So, I just remains for me to close the evening before we go to the bar, that is, and thank a few thank yous. So I would like to thank the team from my organization who made this possible, in particular Mariah Lockwood, who actually made things happen. Sarah Dangle is the other person on the counter who looks after everything that happens, and they made this look easy. So can we give a round of applause to Sarah and Mariah? And I would like you to give a thanks to our video and photograph crew. They will put things up on the web. You'll be able to download them. You'll be able to go and look at them and see all the interesting things that you missed in the other parallel session. So can we thank our video crew for all their work? Thanks very much. And you can have a beer now, all right? The other person I should thank is Harold Javid, who actually worked with our program committee, which was Dan Fay and Chris Toll, who actually put the program together. And so Harold, Chris, and Dan really made the program exciting, and Harold actually made sure that we actually delivered on that program. So can we give them a round of applause, please? Almost done, but I would like to thank the IEEE conference team who actually agreed to participate and to partner with us. And I would be interested in your comments as to whether it's been worthwhile having them together. For me, it's been very interesting. I've seen old friends who I haven't seen since the Global Grid Forum days of 2005. So it's been, to me, very useful to meet old friends and to have a community, a bigger community than just the individual communities. But can we give a thanks to the IEEE team who helped and gave great support. And really, I'd like to thank all of you who gave session ideas, and Dan, Christine were helped by Yan Shu, who put the program together, and all of those who helped in participating in the demos and chaired sessions and led panel sessions. So a last round of applause for them. And the last thing is to thank you all for coming, and I hope you have a great time. And the next meeting of the IEEE meeting and Microsoft eScience meeting is in Beijing. So I'll see you all there. So enjoy the evening. Thank you very much.